In this project, a three-dimensional CFD simulation of a four-layer plate heat exchanger is investigated by ANSYS Fluent software. A steady hot and cold water flows enter the planar domain and move through the heat exchanging region. These flows exchange heat, which leads to temperature difference reduction. Both flows exit the heat exchanging domain with approximately equal temperature, which is 282 Kelvin. The geometry of the heat exchanger is designed in Design Modeler software, and grid generation is done in ANSYS meshing software. Inlet and outlet boundary conditions of both hot and cold flow are shown below. The mesh type is unstructured, and the total number of elements is 2,273,000. The simplest complete models of turbulence are the two-equation models in which the solution of two separate transport equations allows the turbulence velocity and length scales to be independently determined. Robustness, economy, and reasonable accuracy for a wide range of turbulent flows explain its popularity in industrial flow and heat transfer simulations. In this simulation, we prefer to use the standard K-epsilon two-equation model. As you see, the thermal condition is different and it is a coupled wall, or in other words, let's say by using coupled wall we have the conduction between behind and in front of the wall, but there isn't any mixing of the flows because there is a wall between them. And at last we get to the last wall, which is the wall shadow. It's just the same as the wall, so it has a coupled thermal condition. ANSYS Fluent offers us 4 different pressure velocity coupling schemes. The pressure-based solver allows you to solve your flow problem in either a segregated or coupled manner. The simple algorithm uses a relationship between velocity and pressure correction to enforce mass conservation and to obtain the pressure field. We have also employed a standard for pressure discretization and also second order upwind for discretization of momentum equation because of its higher accuracy. Now we get to the primary convergence criteria, I mean residuals. After each iteration, the solver records the values, so the reported value in the console part represent the differences between 2 consecutive iterations. If the values gets below this absolute criterion we define in this window, the calculations will stop. Now we are done and we can run the calculation, but we need the initial values for the calculation. So get to initialization section and use standard initialization to compute the initial values of the calculation, and then directly get to the run calculation to run the simulation with appropriate number of iterations. So when the calculations are done, we can get to the post-processing section. As you know, we've got many options in results section in graphics. We can display a contour, vector, or path line here, but before that we had a 3-dimensional geometry and we need to create 2D planes to put the contours on it. So let me teach you how to create the planes, then you will be able to do whatever you want. So to do that, on the upper toolbar you can see that surface part, click on create and then plane. Then you should choose the method. For example, I want to create the plane in YZ direction, so I should enter the X distance from the origin. So by using 0.03 meter, I can have a plane in YZ direction with the distance in X direction of 0.03. So by just clicking on create button, I can have that. But for the other parts, we do the same. So as you see, we've got 5 different planes for different parts of the geometry, so we can easily get to the contour section to draw on. So when the settings window pops up, we've got a vast list of different parameters here, so you need to just select the whatever you want. For example, I start from the temperature, which is important in this simulation, and in the surfaces box you've got different boundaries plus the created surfaces. So as you remember, we had defined different planes here. So for example, if I click on the X2 plane and save a display, you can see the contour here. And just like the others, for example, I can have the contour of temperature on X2 and also Z5 at the same time by just selecting both of them simultaneously. So here it is. You can see that temperature distribution along the Z5 plane, and just by changing the variable you can get to the other parameters. For example, if I want to display the velocity, I can just change the variable and display that. And here is the velocity distribution. Also, we can use the vectors velocity, and the settings window is very similar to the contour, so there is no need to describe that. But for example, we have the vectors just for the velocity. So by selecting velocity on, for example, Z5 plane and display that, you can see the velocity vectors. For example, they start from here and get to the other part. But you have many settings here to just make them appropriate for post-processing and use in your reports by changing the style, scale, and you can also decrease the number of them by increasing the escape part. So let me just make them smaller and have more of them, and you can see that the changes. And notice that you have many options in color map options related to the colors. It also needs to be mentioned that in order you need to report any parameter or check it, you can get to the report section, and by using surface integrals you can have different types of the report. So for this simulation I prefer to use area weighted average report, and in the field variable drop down list, for example, I can have the temperature because I want to report the temperature at the outlet. So after using the temperature in drop down list of the variables, I should select the surface which I want to report on it. So find the outlet, for example the outlet of the hot water, and by selecting the compute button you can see the area weighted average of temperature at the outlet boundary, which is 281 Kelvin. It also reports in console section. So just like this, you can have different variables on different boundaries and report that in order you need each of them. After the simulation, the results including temperature and velocity contours are obtained for each of 4 layers. Layers are planes parallel to the XY plane which are assigned 1 to 4 as increase of their Z. Layers 1 and 3 are regions where the cold flow is heated up, and layers 2 and 4 are regions where hot flow is cooled down. Hot flow's temperature at inlet and outlet is 286.2 Kelvin and 281.21 Kelvin respectively. Cold flow's temperature at inlet and outlet is 276 Kelvin and 282.72 Kelvin respectively. I hope you find this tutorial helpful. To benefit from Master CFD services including simulation, consultation and training, visit our website via www.master-cfd.com or contact us via info@master-cfd.com.